Today, my plan is to discuss on an example the relation between perturbative renormalization theory that we discussed at one loop in quantum field theory, and the relation with the Wilsonian point of view on renormalization that you have seen in the statistical mechanical course, statistical mechanics course. So I'm not going to do an extensive discussion, but I'll give you an example which illustrates what's going on. So let's say perturbative renormalization in quantum field theory, and why it's related, and in fact, another point of view of real space Wilson renormalization in statistical mechanics and condensed matter. Okay. So, what we did, remember, what we did yesterday was to discuss in detail how you can define a continuum limit of an Euclidean quantum field theory in 4 dimensions, starting from a theory with a microscopic cutoff, so a high momentum scale cutoff lambda, that we want to send to infinity to get something that doesn't depend on the way we have changed slightly the physics at very high energy in order to make sense of the path integral. So we can let me write here that something which is the energy of the momentum scale. Okay, and we study the physics at some fixed energy scale, which is the renormalization scale, at which the physics is defined. We are interested into physics at this energy scale, and we want a theory that defines, for instance, that depends on the, if it depends on the coupling constant, GR, we have GR naught, which is the coupling, the renormalized coupling that characterizes the strength, that quantifies the strength of the interaction at this energy scale. And we have seen that the renormalized theory is such that if we define at another energy scale mu, we study the same physics, we observe that we have an effective coupling or running coupling constant, which tells us what is the typical strength of the interaction at this energy scale when it's compared to this one. Okay. And we have seen in some examples that when you go to the cutoff and integrate the equation of renormalization group, the dependence of GR with mu is given by the renormalization group flow equation. We are going to get some renormalized coupling at the cutoff scale, which may be much bigger or much smaller. In the case of phi4, it's much bigger than the coupling at this scale because it contains a log of lambda. It's much, much bigger. And that's the coupling at the cutoff scale. So that's the coupling that you have to plug in the path integral, in the functional integral, when you define the functional integral in terms of a regularized theory with a cutoff lambda. Okay? So you are interested in what's going on here. You start from this and you see how you must adjust what is the coupling at the cutoff scale, which defines the path integral. So we go this way in a QFT. And so this is a QFT point of view. And in the statistical mechanics point of view, it's rather the opposite. You start from a theory which defined at the scale, for instance, of the atomic lattice. So you start from a microscopic scale. For instance, the mesh of the lattice, the distance between atoms. So let's call this A, and so the corresponding momentum cutoff is 1 over A. So we start from some physical microscopic couplings. Okay, let's call them G. That depends on the microscopic physics, the interaction between the atoms in your crystals, etc., or interaction between the spins that comes from the spin exchange energy in a magnetic material that comes from the physics of how the electron behaves in the crystal. And you are interested in what's going on, what is the effective coupling at a large scale, L, much bigger than lambda, much bigger than A, which means at an energy mu much, much bigger than lambda, which is 1 over A. So in condensed matter or in statistical mechanics, one starts from this and one is interested in what's happening there, while in high energy physics, we start from what we have observed there and we are interested in how does it behave. And does it behave consistently there? Because usually we know the physics at low energy and we want to know what's happening at higher energy. Okay. But that's just, two ways to study the same question, which is how does the couplings or the parameter of our model depends on the scale. And simply in high energy, we want to get rid of the cutoff scale, or at least push it at a scale where we know that the physics we started from breaks, for instance, the Planck scale, while in statistical mechanics or in condensed matter, this is the input, the ab initio data. You cannot change the size of an atom, but you are interested in what's going on there. Okay? But it's just two ways to view the same things. So I'm going to try to illustrate that on a renormalization group calculation, where I'm going to use this Wilsonian point of view, but using some techniques that we have met in this QFT lecture. So I'm going to present a renormalization group calculation which is based on what is called the local potential approximation. I'm going to explain briefly what this is. So we are going to start from a theory given by some action. So let me call this action A. Okay. It was S, but now it's A. Okay, so it depends on some field phi, some local fields, okay? And it's just a generalization of the phi-4 theory, but we just had a general potential V of phi. So, well, you can choose anything, but I'm going to consider a V of phi, which is a polynomial. So, for instance, it's going to be a constant. Well, just to check my notations, but since I'm often changing notations while I have no notation. Okay, so let me just write that this is some constant V0 plus V2 divided by 2 phi squared plus V4 divided by factorial 4 phi 4, but then I allow phi 8 plus etc. And I may stop at some point. So for simplicity, here I have taken an even potential. So V of phi equal V of minus phi, but this is just not necessary. You may do all what I'm going to do can be done with a potential with odd terms, for instance, adding an external magnetic field. Okay? And so I have a potential which has this kind of shape. It's some function, but it can be of a quite complicated function. You see? Okay? Good. Okay. And, well, I'm either in this framework or in this framework. Namely, I am going to introduce a cutoff to define the theory. So I'm going to introduce a sharp cutoff, so that all the momenta are supposed to be less than lambda in my calculation. And I define my theory through Euclidean path integral, where this is exponential of minus a of phi. Okay? Yes?
So the fact that you use a sharp cutoff means that you break everything in Poincare invariance, right?
No. I don't break Poincare invariance. Well, I am in Euclidean setting. Okay, Euclidean. So this is. But this means simply that I'm cutting out the higher modes of the theory. So this means that when I integrate over the field phi of x, I can decompose them into Fourier modes. K dot x divided 2 pi to the power d phi hat of k, and I just do the integral for the k less than lambda. So in other words, the modes, the Fourier modes are 0 if k is larger than lambda. And you can check that these are...
Like symmetry algebra is conserved and it's still unitary and everything?
No, there is no unitary. Well, I am in the Euclidean setting, which means that unitarity has to be replaced by something else. But there is something else in an Euclidean theory which replaces the unitarity, which is called reflection positivity. So there is some axiom. Okay. So here, the unitarity will be problematic in such a theory with such a regulator. But it's still Euclidean invariance. So the Euclidean invariance, symmetry, I think is still okay. Because you can still rotate, and you can still make a translation. Mean a translation means simply add k equals 0, change the k equals 0 momentum of your field. Am I right? I think so. Okay, so this is okay. But unitarity in an Euclidean setting is problematic. You cannot, well, there is a French saying which says that you cannot have the butter and the money of the butter. That's the kind of things. You cannot have the money, the butter. You can get the butter and the money for the butter, which means you cannot get some butter and keep the cash that you used. It's just, so you cannot get an ultraviolet finite theory and still keep all the properties of the continuous theory. Just that. Okay. Good. Okay, so now let us let me remind you what are the idea behind the renormalization group Wilsonian on the. So what I'm going to do is, so you see, in this theory, in momentum space, this is K space. We have a ball of radius lambda in which the momenta are defined. So this is a ball of radius lambda where the phi hat of K are defined. Okay, so there are no momenta outside this ball. Okay? Okay. So now the idea of the renormalization group procedure a la Wilson is to separate any field phi into fast mode. So I take a smaller ball with radius lambda prime less than lambda. And in practice, I'm going to take lambda prime, which is lambda times 1 minus a small. So let me call this d of little s in practice. I'm going to take an infinitesimal mass. So this is what is called, this is a momentum shell. Okay? And I'm going to do what you did in the statistical mechanical course. I'm going to separate phi k into phi fast of k plus phi hat slow of k, where the phi fast are the component with k in the momentum shell, so k between lambda and lambda prime, and the slow modes are the k less than lambda. Nothing. Okay? And the renormalization group procedure means that I'm going to integrate.
Lambda prime?
Pardon? Lambda prime, where this lambda prime is this one.
Yeah, in the second.
Yes, I am sorry. Yes, yes. So thank you. Yes. Okay. And I'm going to integrate, as you did, over the modes in the momentum shell, over the fast mode. So, over the fast mode. Okay. So, instead of integrating over all the modes, I integrate over the fast mode with the original action, and then I get some effective action for the slow modes. That's a general feature. It may be very complicated. Okay? So this is step one. Step one. Integrate over the fast modes. Okay? Okay. But now, of course, this theory is defined in terms of a theory with a model with a new cutoff. lambda prime. So step 2, rescale things, rescales position and momenta, and the fields, and phi slow, so that we recover a theory, a model, with cutoff lambda, so that we can compare this theory with the one we started from. So we integrate over the file mode, we get an effective theory with cutoff lambda prime. Okay? So of course, this is the easy part. It's just performing rescaling. This is the hard part. That's the renormalization group calculation. Okay? So this is just the general principle. So in some sense, this could be considered as some exact normalization group. Okay? It's often called ERGE, come from Wilson. Okay. So I'm going to show you how one can perform such a calculation that, in fact, you did already for some model in the statistical course, in a space form of some local potential, something called the local potential approximation. Okay? So what is the LPA? It's called LPA. So what is the LPA approximation? Consists in I'm going one version of the LPA, which is explained in my lecture notes. And in fact, this is going to be some version of something more general called the renormalized effective potential method, which is something slightly different from Wilson. Okay, so it's a special case. So what I'm going to do is that I'm going to assume that in my calculation, so I'm going to do two approximations. First, I'm going to assume that in my calculation of the effective, I'm going to keep only the one loop terms, keep only the one loop terms in the functional integral calculation. Because integrating over the fast mode is just a special case of integrating over all the modes that we did. Okay. This can be justified. The other approximation I'm going to do is to assume that my A effective of phi fast, phi slow, just is, if you want, projected onto the same form we started from. So it should involve d phi squared for the Slough modes. It should involve powers of phi small, so it should involve basically some v effective for phi slow modes. But I assume, and it turns out that it's not a bad approximation, that I can forget about terms like u of phi slow times d phi slow squared. So for instance, a phi squared term times phi slow, or d phi slow to the power 4, or d squared phi slow squares, so terms involving more than two derivatives of the field, etc. So all those terms are neglected. Okay? Okay. So this is, of course, a truncation of the equation. So we have to check whether this truncation is a good approximation for the physics of the model or not. So to be checked. Okay. But keeping this means that we are considering a renormalization of a theory which is slightly in a bigger space of theories than just the phi-4 theory of the Landau, Ginzburg, Wilson theories that you have been studying in statistical mechanics. So this is a larger space of theory, than just Landau, Ginzburg, Wilson, phi-4 theory. Okay. Good. So now, let me just, without any full justification, give the results of this calculation and try to convince you that it's a good approximation. Okay. So remember, we start from a theory which is of the form A of phi, action which is written there. Okay? Now remember, for a full-fledged QFT, we have seen that the effective action for the background field is the original action. In my notation, this is going to be A of phi instead of S of phi, because now I am denoting by S. And then the one loop term is 1/2 of trace of log of the second derivative of the Hessian, the operator, the second derivative of the action with respect to phi. So this is the Hessian. Okay. And then you have higher looped contribution. Okay? That's the result we derive. And for our theory, with the action is given upstairs, the Hessian of phi, we computed it in the case of the phi-4 theory, remember? It's just to take two derivatives with respect to phi of the action, which involves 1/2 of d mu phi squared plus d phi squared. So we get first minus the Laplace operator. So delta, this is delta is d over d x mu, d over d x mu. This is the Laplace operator. And then we get second derivative with respect to phi of the potential V of phi. So of course what we are going to do is the second derivative of the potential of the function phi. So this is a multiplication by a function, and this is derivative. So in some sense, this operator, what does this mean? This means that head dot of phi, when you apply this to a function psi, taken at a point x, what you get is the Laplacian of the function psi, the second derivative of psi with respect to x evaluated at x, plus psi of x multiplied by the value of the second derivative of v of phi evaluated at the point x. That's just a reminder of what the Hessian is. Okay? And of course, in our case, the second derivative of phi is going to be v2 plus v4 divided by 2 phi squared plus v6 divided by factorial 4 phi 4 plus etc. Okay, so it depends on our coupling constant. Okay. So now, since I'm going to neglect all terms that involve higher derivative, I want to estimate what is the value of this operator if phi is a constant. So what's happened for these terms? So this was my third blackboard. The question is, if my background field phi of x is just a constant, so it doesn't depend on does not depend on x, and this is going to be justified in my next calculation because I'm interested in what's happening for the slow modes when I'm going to integrate over the fluctuation of the fast mode. So in some sense, if I separate the fast and the slow modes, the slow modes can be viewed as constant background for the fast mode. It's a bit okay. So I consider that phi of x in this calculation is just a constant. So then, of course, trace of log of the Hessian of the action for this phi, the trace is just the integral over space, and we are considering the matrix element between x of the operator log of the second derivative of phi. Okay? Okay. Now, if phi is independent of x, is a constant, then this operator, the Hessian, is just an operator which is invariant by translation, because this is a constant. This plays the role of the mass term. So, second derivative of phi is just minus delta x plus of phi, which is a constant. So it commutes, it's an operator that commutes with the translation. Is it clear? So it can be diagonalized in the basis of eigen vectors for the translation, which are the plane waves. Okay. So in other words, if we go in Fourier space, transform, if instead of writing this operator as acting on psi in the x representation, but in the p representation, so as acting on the Fourier transform of x, we get that in this case of phi is just multiplication by k squared plus the same constant. So acting, so So I consider that acts on function psi, the Fourier modes of the function, test function psi. Okay. So this is the eigenvalues of A, k squared plus second derivative of phi. Okay? And therefore, the log is just, you can diagonalize, and what you end up here is that each of these elements, it doesn't depend on the point x because of translation invariance, so it's just a pure number, and this is just integral over dk over 2 pi to the power d, and the log of k squared plus second derivative of phi. Okay, for all momenta. So this is this element, and then therefore we still have to integrate over x. Okay, so this is an exact formula for the trace of the log of this operator when the field is constant. Okay, it's exact because we know how to diagonalize this operator, so we can compute the trace. Okay. So then you see you have an integration over the position, which is okay because we are computing the trace of a log-on operator, so it has to be extensive. If the volume of space-time is twice larger, this term has to be twice larger. So this is just extensivity. Okay. And that's the integration over the modes, sum over the eigenvalues. Okay. Okay. Yes?
I'm a bit confused why the result is not just the k integral. Like I would expect the trace to be just the sum of the eigenvalues in any basis.
There is not only a k because it's a question of normalization of the eigenvalues. You can view also this as a normalization of the eigenvalues. The best way to do that is to regularize everything. You take a lattice, with a mesh A and a size L, and with periodic boundary conditions. Periodic boundary condition. Then the eigen modes of so basis of momentum k, or the k function, let's say k, are just a function exponential of I k x. Okay, but of course the momenta x has to live on the lattice. So x is of the form I times a with I some integers, but living on the lattice this times L z to the power d. So it's a periodic L divided by a. So let's get n, where n is L divided by a. That's the number of sides. And the momenta are quantized too. So the momenta have to be of the form. So the momenta have to be of the form, if I'm not mistaken, 2 pi over L, no, yeah, times some number G. with G also belonging to this lattice. So both the momenta and both the space and the momenta are quantized because space-time is a torus, so its conjugate space, Fourier transform, is also the torus. And then there is a factor here, a normalization factor, because you want that k prime equal delta of k minus k prime. So you have to sum over all the sides. So you get a factor 1 over n, square root of n. And n is L divided by A. So when you compute the trace of the log involving this, and then the eigenvalue, you know what it is. The eigenvalue for a momentum k with this is that, eigenvalue lambda k. So it's just a discretized version of this where the momenta are quantized. So it's, well, the k squared is replaced by a sine squared of k mu times A. I think I think this is one, this is okay. Divided by 1 over A squared, sum from u equal 1 to d, plus you do the calculation. So the k squared, so k squared is replaced by this quantized momenta in a Brillouin zone. And when you sum over the k, you take the trace with this matrix element. You have this. You have an n factor that gives you the n. So this is good. You get a term which is proportional to the number of points. Okay, that's an answer. Okay. I can give you the detail of the calculation. That's a nice exercise to do. Okay. But it comes basically from the fact that in the definition of the trace, this is integral over x of some matrix element between x. And it is this matrix element which is proportional to this integral over k. Okay. Okay, so this is the results. In fact, this effective action that we were interested in. Where was it? Where did I write my effective action? Oh, it might be just here. So this term, yeah, here it is. Right. This effective action is obtained where we integrate over all the momenta. Of phi. So we integrate over all the fields. But remember, we have this momenta k, but our momenta originally belongs to the big ball of radius lambda. So if we integrate over momenta that belongs to the ball k between lambda, of course, here we have to integrate over momenta k less than lambda. We have regularized our theory, so we have regularized it in momentum space. We use the sharp cutoff in momentum space. So the integral over k here is restricted to the momenta less than lambda, and that's something very important. Okay. But the integral over x is over all space, because space is not quantized in this theory, and as you said, this is still transversionally invariant. Okay, so we have to make this in. Okay. So from this expression, from this result, which is an exact result, we can guess, and I'm not going to do the calculation, but we can guess that out of that, one can show that now, when integrating only on the fast modes, namely the phi fast, which depend on momenta k between lambda and lambda prime, the integral should be replaced by the integral over the momenta where k is between lambda and lambda prime, because we are integrating only on the high mode. So we can guess that from this formula, well, let me write this on the next blackboard. The result of the calculation for A effective of phi slow in what I call the local potential approximation is just the classical action A of phi slow plus a contribution that comes from integration over the fast mode, and the contribution over the fast mode is going to be simply 1/2 integral dx integral d dk over 2 pi to the power d times, but I integrate over the momenta k between lambda and lambda prime, okay, times log of k squared plus second derivative of phi at the point x. And if you are worried by the fact that this is a log of something without dimension, just divide by lambda squared, which is the only scale we have in our calculation. Okay. So this is the result. I'm not going to derive it, but if you make precise, if you formulate in a precise statement what are the approximation we use, here, the fact that we are using only the one loop approximation and we are projecting out of this space of function, this is a result which is solid. Okay, so there are approximation, but within this approximation, this result is solid. I just wanted to show you where it comes from. Okay. Okay. So this is an explicit result. You see that you have an explicit expression for the effective action in terms of the potential we started from. And you see that this is a function of phi of x. So this effective action has the same form as the action we started from. We can write it as integral dx 1/2 of d mu phi slow squared plus some effective potential of phi slow of x, where the effective potential of phi slow is just the initial potential we started from plus this term. So this is a new effective potential. And you see that you have an integration over k, but this depends only on phi(x). So it's a complicated function of phi(x) that we can compute. Okay. Okay. So now the calculation becomes simpler if you integrate over just a small momentum shell. Because if you make a small momentum shell, so small momentum shell, where we integrate between lambda and lambda times 1 minus ds, this integral becomes an integral over momentum shell, so basically k squared is over the lambda squared. So then V effective of phi slow is V of phi slow. It's a function, it's not a functional, so I should have just written parenthesis and no bracket. And then this is the value of this integral, the integral over the momentum shell. So the integral over the momentum shell, we just integrate over a sphere, a d-dimensional sphere, a sphere in d dimension with width epsilon. Okay, so we just get a term of order, well, we get 1/2, we get ds, the width of the frame. You get a term which is proportional to the volume of the sphere. So we get a lambda d. Lambda d divided by 2 pi to the power d. We get a volume of the sphere, which is a factor 2 times pi d over 2 divided by gamma over d over 2. This term is a volume of the d minus 1 dimensional unit sphere. So the unit sphere in d dimension, which is a d minus 1 dimensional manifold. And then we get just log of lambda squared plus this divided by lambda squared. So we get log of 1 plus 1 over lambda squared, second derivative of phi slow, which is a much simpler function. Okay, so it's a function which is not a polynomial in V slow, it's a log, so, but it's okay. So, okay, so keep in addition this term. So, within the LPA approximation, step 1 is done. We have an explicit expression for the effective action of the theory once we have integrated over the fast mode. Now we have to perform the rescaling. So, third step, now the rescaling. Step 2. Okay. And so here I just need to be careful because usually I made mistake. Okay. Okay. So of course, now the rescaling is that we have to define, starting from the momenta k, we have to go to momentum k prime, which is k times 1 plus ds. So that the new cutoff is lambda prime well, it's a bad denomination because I have a prime. Let's call this K bar. So that the new cutoff, K bar, is the whole cutoff of for the series for lambda prime times 1 plus ds, but lambda prime is lambda 1 minus ds, so this is lambda. Okay? But this means that we have to rescale the distance in new units, where x prime is x times 1 minus ds. Okay? And in these new units, the volume term changes because d dx becomes d x prime, well, d dx bar, it becomes d x bar times 1 plus d times ds in the path interval. If I make this change of variable, dx becomes this, but also d over dx mu becomes d over dx bar mu times 1 minus ds. And so you see that you have to change the definition of phi slow. You have to make a renormalization, a rescaling, let's say, because rescaling of the field phi, so that phi slow of x, I recall this as phi bar of x bar times, and I have to absorb this d and this minus for the two derivatives. So this has to be 1 minus d minus 2 divided by 2 times ds. So you have to rescale the field. That's important. That's rescaling of space. And that's the rescaling of field. Okay? And with this rescaling, which is just a change of variable, my A effective of phi slow, I just re-express it. So I re-express it as A renormalized of phi bar. And this A renormalized of phi bar is integral d x bar of 1/2 d over dx bar mu of phi bar squared plus a new renormalized potential of phi bar. Because if I made a change in phi, everything amounts to a renormalized potential. Okay? And now it's easy from this to check that V renormalized of phi, well, I omit the phi bar because, okay, is just V of phi, the original potential, plus a modification of order d little s, this d little s here. And then you are, of course, you are going to have this important term, but you are going to have terms that come from the rescaling of x and the rescaling of phi. So what you get is d times v of phi minus d minus 2 divided by 2 times phi times the first derivative of the potential with respect to phi. This is just the derivative of a function v of phi. And then you get these terms that I'm going to write some number A that depends on the dimension times the log of 1 plus 1 over lambda squared, the second derivative of phi of the potential. Okay. And this is a log, and so this is a full coefficient in front of ds. Okay? So this comes from the risk. In fact, this comes from the rescaling of x. This comes from the fact that we have rescaled the field. So this comes from the x rescaling. This comes from the phi rescaling. And this comes from the difficult step 1, the renormalization calculation. Okay? So now, this is something, this result, which is important, is nice. Because it tells you how the potential gets renormalized when you make an infinitesimal renormalization group transformation. Okay. So now you can integrate by you make a renormalization group transformation by an amount ds, and then you can do it n times, so you get a renormalization by a big factor s. Integrate this. And if you do this, you get renormalized potentials that are going to call Vs of phi, which is the renormalized potential after a scale transformation by a factor s. So I went from some scale to scale x to sx. So a factor s in position space. In position space. So this is a scaling transformation by factor s in the sense of the Wilson calculation. And of course, this is just the infinitesimal formula for this s. So this becomes a differential equation for V of s. So you see, V depends on phi, and now it depends on s. And the renormalization group flow equation for V s of phi is just given by this term. So let me write it again, because it's important. It is S d over ds of Vs of phi. It involves the derivative with respect to log of s, because if you integrate, you have 1 minus ds, and then you have 1 minus ds times 1 minus ds. So ds is a logarithmic variation in the cutoff. So this is s d over ds of Vs, and this is just d Vs of phi minus d minus 2 over 2 phi V prime s of phi plus this coefficient AD times log of 1 plus 1 over lambda d, the second derivative of Vs of phi. Okay. So it's exactly the same equation, but now written as a differential form. So let's keep it. Okay. Is it clear? And this coefficient AD is just the big factor here. So let me write it somewhere, because it's interesting when you are going to compare to the results. So AD is, if I'm not mistaken, this is 1/2 well, I, of course, yeah. AD is, oh, there is a lambda D, I'm sorry. There is a lambda D here. By dimensional consideration, lambda D. No, here this disappears because of the rescaling. Okay, so that's okay. So it is AD, and then we get 1/2 1/2 pi d 2 pi d over 2 divided by gamma of d over 2. So this is, if I'm not mistaken, 1/4 pi d gamma of d over 2. Okay. And, well, no, there might be a lambda. No, there is a lambda. In fact, there is a lambda that stays there, but that's not very important. Okay. Lambda is fixed. It's a starting point we started from. Yes?
Where does that S come from? You have a prefactor S there. Like you have basically
No, the capital,
minus
the
V.
capital S is that just I want to perform a renormalization group calculation, you see, from, I'm sorry. The idea is that, no. I want to perform a renormalization group calculation starting from a cutoff lambda
I know the interpretation of S.
and go to lambda divided by S, to a cutoff lambda divided by
The
S.
question is, you have there an equation which is basically Vs
Yes.
equals V plus ds of stuff. And then you rewrite that to a differential equation, which means you put V to the other side, you have Vs minus V
No.
divided by ds.
No, what I'm just rewriting is that V renormalized is, so V renormalized is a renormalized potential for a scaling factor which is 1 plus ds. Okay? And I am rewriting this as V of 1 plus delta V times ds. So delta V. So this is V1, the original V1 plus dV over ds delta S.
Yeah.
Okay, so
And
if I put this
V1 is
here,
already in there, and
I
then-
just get that delta V is delta S times
that stuff. So why is there
what I wrote here.
prefactor S?
What?
In your differential, you have d over ds, but there's a prefactor S there.
Here.
It doesn't set, yeah, that S. Why what is it doing here? Where does it come from?
It comes from the fact that first I went from lambda to lambda divided by 1 plus ds. My d little s. Okay? So this is an elementary transformation. If I do this n times, I do lambda into lambda times 1 plus ds to the power n.
Since when are we doing the transformation n times?
Because it's the idea, if you perform a renormalization group transformation, a small renormalization group transformation n times, and you iterate it a large number of times, you get a finite order.
We don't want finite results. We're trying to get a differential equation, which is a local thing.
But that's what I did. No, what I'm simply stating is that when you go to S, from S to capital S plus delta capital S, you can write this as S times 1 plus delta S divided by S. You see? And this is the delta little s that I'm being considering. So here I started from a scale 1, and I went to 1 plus ds. But if I iterate it n times, little s corresponds to the variation of a log of s.
So the big S was 1 before.
I started from 1, but if instead of 1...
And you're taking a small step away from 1, not a big step, a small one.
But now I can iterate. No, imagine that imagine that my v, now, my v of phi, now is vs of phi. So I have performed the renormalization group transformation from scale 1 to scale s. And I get a potential, so I start from a potential V, I get a potential Vs. Okay? Now I want to go from V to S plus delta capital S. And I'm going to get a potential here, V of S plus delta capital S. For this, I did my calculation. Why?
That is not where you did the calculation. The calculation goes around 1.
My calculation doesn't depend on the potential I started from, and doesn't depend on the...
But then you have a new lambda and everything.
What? No, because at each step, lambda is rescaled to be the same. You see, we integrate and we rescale. So here and here the cutoff is lambda, here the cutoff is lambda, and here the cutoff is lambda. That's why the rescaling transformation, the step 2 is needed. Because otherwise we cannot compare two theories with different cutoff, two models. Well, think a bit about it, and you'll see. And you'll see that this corresponds to what was done in the statistical mechanism course. He used a different language, I think, but this rescaling is there, explicitly or implicitly.
Yeah, sure.
Okay.
Rescaling is there, yeah.
So rescaling is there. So the cutoff doesn't change in this renormalization group transformation, because if we make a block spin transformation or an integration of the momentum shell, then we rescale everything to go back to the theory whose parameter I express with respect to this cutoff. So the cutoff doesn't change, but the theory changes. Okay. So here, what I did was to go from this to 1 plus delta little s, and then I get a V renormalized. But the calculation which is valid here is obviously valid here, because at the same calculation, we just start from another potential. You see?
Why are you making different steps
Huh?
as you go? Like, why are you making different size of the step as you go?
I don't need. Well, you can choose whatever you want.
Okay, sure.
But just take this calculation, and you see that if you start from S and go from S to delta capital S, this can be rewritten as S times 1 plus delta capital S divided by capital S. So if I do my calculation going from V of phi, see if now my initial V is Vs of phi, and I go to Vs renormalized of phi, the corresponding, in my calculations, the corresponding little d little s is just d capital S divided by S, simply because S plus delta capital S is S times 1 plus delta S divided by S. I'm just stating that if you make a strike scale transformation, if I make a scale transformation that goes from 1 to 2, and if I perform the same scale transformation, I do not go from 2 to 3, I go from 2 to 4, then to 8, if I get a scale transformation. So the group of scale transformation involves the logarithm is additive. It's additive in log of the scale factor. Say, if I make a scale transformation by a factor s, let's call it Rs. This is an expression for scale by s. If I make a scale transformation by a factor s1, and then I make a scale transformation by factor s2 applied on my system, of course, what I'm doing is a scale transformation by a factor s2 times s1. So the additive parameter when you iterate scale transformation is not s. So if this is nu s, it's log of s nu is log of s1 plus log of s2. So if you want to write your renormalization group transformation as a differential equation by seeing what's happening when you iterate small scale transformation, the parameter that enters when you write it in an additive way is not the scale factor, it's a log of the scale factor. It's just this very elementary fact that you rescale by 2, then rescale again by 2, you have rescale by 4, not by 3. Okay? So there is a SDDS. Okay, well. So it's not completely, no, I agree, it's not completely obvious, but it's once you have understood this is simple. Okay, so now I have 10 minutes left. So now let me just show you what this equation contains and what we can make out of it. Or perhaps I can just, okay, so the idea is now that we have this equation. Well, I can erase this, I think. So let me use the middle equation. So this was 1, 2, 3. This was 0, 1, 2, 3. This was 4. This was 5. Just remember where I am. So I am erasing 2. And let me see what this equation gives. When you take, so now, when you take an explicit potential, the one that I wrote here, so now explicit calculation, explicit renormalization group flow out of this functional equation. So I start from V of phi equals V0 plus V2 divided by 2 pi squared plus V4 divided by factorial 4 phi 4. So if you start from this equation, then, of course, you get an equation where V double prime of phi is a polynomial in phi. It's a simple polynomial in phi. It's V2 plus V4 divided by 2 phi squared, but then log of basically 1 plus second derivative of phi. Well, you can normalize everything so that the cutoff is 1. It's just a normalization. Is of course a log of V2 plus 1/2 V4 phi squared. So it's going to be a constant log of V2. Oh, and but there is a 1. Okay, so there is a log of 1 plus. So it's log of 1 plus V2 plus log of 1 plus 1 V4 over 2 1 plus V2 phi squared that you can expand in a term V2 plus a term V4 plus a term phi 6, etc. So you see in this randomization group calculation that if you start just for the phi 4, you generate phi 6. So if you start from phi squared and phi 4 term, then randomization group transformation generates higher order terms. So this exact flow, in a sense, lives in the space of theories with an arbitrary number of poles of phi. Okay, but you can make a further approximation. Truncate to phi 4. So forget about this term. And you get approximate flow. Get flows truncated at order phi 4, but then you can truncate them at order phi 6, etc. So you can play in a systematic way. And I'm just going to show you now the result of the calculation briefly, because we still have just 5 minutes, so I'm not doing any calculation. So I try to show this. Thank you. Can you dim a bit? Oh, this should appear soon. Cut down on. Okay. So this is just first on this first slide is just rewritten the flow equation, and I wrote it in 4 dimensions. So this is the d equal 4 case. In the d equal 4 case, this is 4. This coefficient is 2, is 1, and a, which is written there, is 1 over 4 pi squared. This is a d minus 2. There was a typo. Okay. So now, okay, I start here. Okay, here I truncated to order phi 6. So I start from a potential that contains terms of phi up to phi 6. I wrote this equation. I expand it in phi, and I forget about the term of order phi 8, phi, etc. So then, of course, Vs of phi is going to be of the form V0 of S plus V2 of S over 2 phi squared plus etc. And here, instead of V2, V3, V4 in these notes, V2 is T, V4 is G, and V6 is H. Okay, and that's because T and G were the notation used in part of my lecture notes. Okay, so you are going to find that in the lecture notes. So you do the calculation, and you find for the equation for S, this 2T plus some G times something. For G, you find 3 over 4 pi squared times T plus 1 squared, plus a term involving the phi 6 coupling and the term involving a coupling of phi 6 and phi 4. And the randomization group flow for the phi 6 coupling, you get a minus 2h plus a term of order G cube and higher order terms. Okay? Okay. So now, remember that what I discussed yesterday and what I discussed also today at the beginning of the course is that it's still written there. Is that in QFT, the beta function that describes the flow in mu means that you see how the renormalized coupling flow with the renormalization scale when you go from low energy to high energy. While the Wilsonian renormalization group flow, you see how the effective coupling constant, the renormalized coupling constant flow when you go from the ultraviolet to the infrared. So it's the opposite sense. So I expect, and I think I wrote that already, I expect that the Wilson functions that tell you how, when I make a scaling transformation in momentum space of some coupling, G of S, should be equal to minus the beta function associated to this coupling of G of S, simply because it goes in the opposite direction. So this is QFT Canan Szymanczyk renormalization group functions. And these are the Wilson functions, which in my lecture notes are denoted WG of G of S, W meaning Wilson. So that's the notation, but these are defined. Okay. And so you can check here, for instance, something interesting. You check that the Wilsonian renormalization group flow. Well, if you are for the massless theory means T equals 0. You get minus 3 over 4 pi squared G squared. So you see indeed this relation. The renormalization group flow, the beta function for phi 4 is minus the flow we get that. Okay? And there are higher order corrections, but that's it. When you include H and G, you see? And if you do the tutorial about mass renormalization, you'll get the same thing for the coupling of T and the same thing for the coupling of H. And you see that here in 4 dimensions, you get a factor 2 because the mass term has dimension 2 in momentum. And you get a minus 2 here because the phi 6 term in 4 dimensions has momentum dimension minus 2. And you get no linear term in 4 dimensions because G is dimensionless in dimension 4 and Z dimensionless in dimension 4 because phi 4 theory is renormalizable in dimension 4. So this Wilsonian-like renormalization group calculation, but using a method of quantum field theory because we relied on the calculation of the effective action at one loop, you see, agrees with the perturbative calculation. I draw no diagram. I haven't drawn any diagram. And a nice exercise is to find which diagrams correspond to these terms. Because there is since the calculations are equivalent, there should be a bijection between the perturbative calculation and this functional calculation. So in fact, you can associate diagram to all of these terms if you are a bit clever. Okay, so now let me just show. Okay, so this equation is not. Now you can study the flow as you did in statistical field theory and see whether the flow to some fixed point or do not flow to some fixed point. And I have no time to discuss that, but simply this picture is to show this picture is to show that in the T phi 4, so this is T, this is G, and this is H phi 6. In this three-dimensional plane, you have a critical surface where the flow goes to the Gaussian fixed point, and you have a surface where the T becomes large and positive, and T becomes large and negative. So these flows contain the phase diagram of the Ising model, where you have a ferromagnetic phase. No, a ferromagnetic phase here where T is negative, the symmetry is broken. A paramagnetic phase where T is positive, so the symmetry is not broken, and a critical surface where phase transition occurs, just. And if you truncate to forget about the phi 6 term, these are the flow in the T phi squared and G phi 4 coupling. So you see that you flow toward the Gaussian fixed point here, but here you flow downwards and here you flow upwards. And finally, that's an interesting feature. Okay, so this is the critical surface. And finally, you can check that. Now, if you are on the critical surface, you assume that this term can be neglected because the theory is massless. So here, this flow illustrates what's happening when you consider the massless phi 4 theory, but add a bit of phi 6 coupling, which corresponds to an irrelevant parameter. Okay? So this is the G coupling for phi 4, and this is the H coupling for phi 6. And you see that if you add a bit of phi 6, which may be dangerous in perturbation theory, the renormalization group flow at large distance drives these terms to 0 very quickly, because there was a -2 coefficient in the beta function for this one. So you are always attracted toward the line where G is non-zero, but T is 0, by the renormalization group flow, namely by the quantum fluctuation. So this corresponds to the fact that the coefficient H in the language of renormalization group is an irrelevant coupling. If you add a bit of phi 6 coupling in the theory with a cutoff, and you let the cutoff goes to infinity in order to have theory, this goes to 0. So you can neglect phi 6 coupling in the low energy theory. So it's just a figure to illustrate that. Okay? So, and I stop there because I already spent a bit more time. Okay, so I hope that you understand better what is the connection between quantum field theory calculation and Wilson renormalization group by this kind of calculation, which are a mixture of quantum field theory methods and Wilsonian ideas. And by this, just this dictionary, which states that basically renormalization in QFT and renormalization in statistical mechanics are just the two ways to look at how the parameter of a theory, the effective parameter of a theory, vary with the scale, either going up or going down in energy. Okay. Thank you. And next time we start quantization of fermions and of gauge fields, the last week.